So like I was saying, low oxygen in the blood is going to help stimulate hematopoiesis, and it does that by stimulating, or the kidneys have sensors on them for detecting low oxygen in the blood, and then that will stimulate the production of erythropoietin, which then goes on to stimulate stem cells to differentiate in the red bone marrow into red blood cells, and then those red blood cells are produced, and then they're put into the bloodstream so that oxygen levels return to normal. And so that's shown on this diagram here. So in a normal blood oxygen level, this isn't happening, but if we're imbalanced, this stimulus, this decreased red blood cell count or decreased availability of oxygen to the blood or increased tissue demands for oxygen, if we're like exercising, it imbalances the amount of oxygen in our blood. Well, so that's reduced oxygen levels in the blood. Kidney senses that and releases erythropoietin, which then goes on to stimulate the red bone marrow to make more red blood cells, right? So those stem cells are already in the red bone marrow. Erythropoietin stimulates those cells to differentiate into red blood cells, which then can carry oxygen in the blood and return us back to normal blood oxygen levels. Leukocytes, these are the white blood cells. They function to protect the body against invading microorganisms and pathogens, and they remove dead cells and debris so that we don't get infections. There are a bunch of different types. You have neutrophils, which function as small phagocytic cells, so they go around eating other cells, or like pathogens, so that we don't get infected. Eosinophils are going to reduce inflammation in the area. Basophils release histamine and increase an inflammatory response. Lymphocytes are involved in immunity. We'll talk about those more when we get to the lymphatic system. And then monocytes become macrophages. And so macrophages are going to go on to engulf pathogens and make sure that they don't cause issues for us. And so we can kind of see that, when you get an injury, neutrophils are the first ones on site, and they'll come in and make sure that they'll just start cleaning up different little cells or fragments of pathogens, make sure they're not going to harm you. Eosinophils are also going to be in there, so those eosinophils come in, help reduce the inflammation. Basophils will be in there, not pictured here, but they'll help release histamine in there. And then you have your monocytes, which come in and become macrophages, and those macrophages go in and do the major cleanup of all the pathogen chunks. So here are your different leukocytes. You have your agranular, your lymphocytes and monocytes, and then your granular, basophil, neutrophil, and eosinophil. If it helps, you can use the mnemonic, never let monkeys eat bananas. So never let monkeys eat bananas. All based on the first letter of all the different words. So if you can just remember, never let monkeys eat bananas, you got the first letter of everything that you need. You just need to fill out the rest. And so we will need to know these physical characteristics for lab, but when it comes to their functions, we need to know those for lecture, and that was on the last slide. So platelets, these are thrombocytes. Their origin is in red bone marrow. The structure is basically a megakaryocyte that becomes fragmented, and little chunks of those cytoplasm fragments become platelets. And so thrombopoietin comes in and stimulates those same cells that could become erythrocytes, but it stimulates them to become megakaryocytes, which then basically explodes in a different process, but breaks up into chunks and becomes little platelets. And these platelets function in repair of damaged blood vessels via platelet plugs, and they provide growth factors for healing and repair. So that leads us to hemostasis. So we know all the players that are involved, and now we just got to discuss the actual process. And so there's a lot going on here, and we'll go ahead and dissect it chunk by chunk. But hemostasis in general is the process of halting blood loss. And so stasis, just like homeostasis, is just kind of like a balance, and hemo is related to blood. So it's balancing blood. And so we're trying to balance how much blood is lost. We don't want to lose any blood, so we got to fix it. So when you initially have a cut, you have a vascular spasm, and then that's followed by a platelet plug being formed, and then the blood coagulating. And those steps are all shown here. So you get a breakage, vasoconstriction, and then platelet activation makes your platelet plug. And this is what's known as primary hemostasis, the initial reaction to an injury. And then after that, secondary hemostasis happens, and that's basically coagulation. So we don't have to know about antithrombotic control mechanisms, but we do need to understand a little bit of the coagulation cascade in order to understand how we get a blood clot so that we can stop bleeding. So a vascular spasm, think of vasoconstriction. So the vessels in there are constricting, they're becoming smaller. So vasospasm, vascular spasm, it's becoming smaller, restricting blood flow from this area back into this area. So we're gonna constrict this area, and it's the smooth muscle inside the blood vessels, which we'll get to when we talk about blood vessels, but it's in this tunica media. There's a smooth muscle layer, and so we're going to constrict the blood vessels, and it'll close small blood vessels off completely, but the larger ones we'll make sure that we just kind of pinch them off. It's an immediate, but it's a temporary solution. So this is an initial response. It's under sympathetic control, so it's immediate. You have no control over this autonomic nervous system, but it helps to not bleed out immediately. Then the platelet plug is also part of that immediate response. You have platelets flowing through your blood for a reason, and this is it. What happens is when you get an injury, the platelets released from your blood that, it's kind of spilling over, they attach to this collagen layer, which is kind of toward the outside layer of your skin. And so this collagen layer has a bunch of fibers sticking out, and the platelets can attach to those fibers. So they stick to that, and that's via this von Willebrand factor. It's a protein that helps stick them to the collagen. And then the platelets secrete chemicals that cause other platelets to stick to the exposed site. And this is the prothrombin activator. And so it's not listed here, but prothrombin activator helps all these. So, you kind of see this is like a black one for von Willebrand. Kind of think of it as the red activator. Prothrombin is, kind of sticking all these guys together. It's actually fibrinogen, but think of prothrombin activator as helping stick these platelets all together. And again, this is a temporary solution, and it's sufficient to stop minor cuts, but we will keep bleeding if we can't fix this completely. So it's sufficient to stop minor cuts, but like a deeper cut will for sure need coagulation in order to heal that injury up. So like a paper cut, this could just be the end of it. But a deeper cut, you'll need to coagulate. And so more sophisticated repairs are carried out by this coagulation, which is the formation of the blood clot. A lot of stuff going on here. Don't get bogged down with it. I'm going to break it down. We're not going to go through all of it, and you don't need to memorize all of this. Just know that basically what we're looking at is down here. So that prothrombin activator was released by the platelets, and this converts prothrombin into thrombin. So prothrombin is kind of just circulating around, and prothrombin activator activates prothrombin, turns it into thrombin, and thrombin then goes on to activate fibrinogen. Fibrinogen is also just floating around. Well, fibrinogen then gets converted into fibrin, and that's via thrombin. So thrombin converts fibrinogen into fibrin. This fibrin can then form a cross-linked fibrin mesh that, in essence, forms our blood clot. And so the result is this production of a gelatinous but robust clot made of this mesh of fibrin. And it's an insoluble filamentous protein that's derived from fibrinogen and the plasma protein introduced earlier, in which platelets and blood cells get trapped. And so this is good because now we can stop the blood. And so here's a really nice video. I'm not going to play it during this lecture. I'll leave it up to you to come back into the lecture slides that I provide so that you can watch it on your own time. I highly recommend it. It's only 4 minutes. It's a great video that he discusses all the steps of hemostasis so that you can understand it further, but it's very similar to what I just laid out. The reason I'm not going to play it is because last time I tried to play videos with these recorded lectures, it did not sound very good. So we're not going to do that again. So fibrinolysis is the act of removing the clot. So the tissue needs to heal, and so in order to heal, we got to remove that clot. So after we've been able to stop the blood flow, the clot can start being removed. They have to be dissolved, and this is via anticoagulants. And so plasminogen gets activated and produces plasmin. So plasminogen, just think of, and there's a lot of stuff going on coming up to this point. Just understand that plasminogen gets activated, which then goes on to become plasmid, and then plasmin can dissolve our fibrin clot. And so we need to be able to hydrolyze or dissolve our fibrin clot so that we can fully heal. Okay, so that's the process of fibrinolysis. Think of glycolysis, just like when we were breaking down glucose, think of fibrinolysis as breaking down fibrin.